Hello, and welcome back to the channel. Today, we delve into a crucial aspect of building robust and resilient modern applications: queuing systems and async design, how modern apps breathe under load. Queuing systems exist fundamentally to introduce a layer of decoupling between different parts of a distributed system, specifically between producers, which could be clients, front-ends, or other services sending data, and consumers, the back-end services that process that data. This decoupling is vital because it allows systems to absorb high-traffic spikes gracefully without immediately crashing downstream services. Instead of direct, synchronous communication that can easily overwhelm a consumer, requests are placed into a queue, acting as a buffer. This also enables sophisticated features like retry logic for failed tasks, task prioritization, handling urgent messages first, and rate smoothing, where bursts of incoming requests are processed at a steady, manageable pace. Queuing systems are absolutely essential for any asynchronous workflow, such as processing online orders, encoding uploaded videos, sending out large batches of notifications, or handling financial transactions. Ultimately, they allow services to work at their own pace, leading to a much more elastic and healthy overall system. To understand queuing systems, let's establish some key concepts. The flow typically begins with a producer sending a message, a piece of data, or a task to a queue. The queue then securely holds this message until a consumer service is ready and available to process it. Once processed, the message is removed from the queue. Messages themselves can have various characteristics. They can be durable, meaning they persist even if the queuing system crashes. They can be delayed, processed only after a certain time, or they can be priority-based, ensuring critical tasks are handled before less urgent ones. The core benefit is supporting asynchronous processing, where the producer doesn't have to wait for the consumer to complete the task. This, combined with load buffering, allows the system to remain responsive even when back-end processing is slow. Queuing systems are often implemented using specialized software called message brokers, such as RabbitMQ or Apache Kafka, which manage the queues and message delivery. This architecture significantly boosts fault tolerance in microservice architectures, as one failing service doesn't directly block others. Messages simply wait in the queue until the service recovers or another instance can pick them up. The landscape of queuing systems offers several powerful tools, each optimized for different use cases. RabbitMQ, a widely adopted, lightweight, and robust message broker, excellent for general-purpose task queues where messages need to be delivered reliably and can be consumed by one or more specific workers. It's particularly strong for implementing complex retry mechanisms and routing patterns. Apache Kafka, a distributed streaming platform designed for high-throughput, fault-tolerant stream processing. Kafka excels at handling massive volumes of data streams, making it ideal for real-time analytics, log aggregation, and large-scale data pipelines where message order and durability are paramount for many consumers. Amazon SQS, simple queue service, a fully managed, serverless queuing service from AWS. It's highly scalable, durable, and eliminates the operational overhead of managing your own message brokers. SQS is a great choice for decoupling microservices and buffering tasks within the AWS ecosystem. Redis Streams. While Redis is primarily an in-memory data store, Redis Streams provide a fast, in-memory async queue capability. They are excellent for scenarios requiring very low latency and high performance, especially when integrated into existing Redis-heavy architectures. The selection of a queuing system heavily depends on your specific needs regarding message durability, strict order requirements, acceptable latency, and the overall scale and throughput your application demands. Queuing systems are the invisible backbone of almost every large-scale modern application. Let's look at some real-world use cases. In e-commerce, when an order is placed, it doesn't immediately trigger all downstream processes synchronously. Instead, the order message is sent to a queue. Consumers then pick it up for payment processing, then for inventory update, and finally for sending the confirmation email. This asynchronous flow ensures that even if one step temporarily fails, example, email service is down, the order itself is still processed and the email can be retried later. For platforms like YouTube, when a video is uploaded, it's immediately placed into a queue. This triggers a separate process for video encoding into various formats and resolutions, which can take time. Once encoded, another message might be queued for delivery to CDN edge locations. In ride-sharing applications, a trip match request isn't processed immediately by a single service. It might be queued, triggering checks for surge detection, and then asynchronously sending driver pings to available drivers. Even in banking, sensitive operations like an async transaction ledger update might queue messages that then trigger a separate service to send a notification to the user. These examples highlight how queues ensure failure isolation, where a failure in one component doesn't bring down the whole system, and enable elastic throughput, allowing the system to scale effectively under fluctuating loads. The absence of queuing systems in a distributed architecture can lead to severe operational challenges and system fragility. Without a buffer, backend services crash under unpredictable bursts of incoming traffic. A sudden influx of users can directly overwhelm your processing capacity, leading to downtime. There's no inherent retry mechanism if a downstream service temporarily fails. If a payment service goes down mid-process, the entire operation might fail permanently, leading to lost data or frustrated users, as there's no queue to hold the message for a later retry. It creates tight coupling between components. If the client producer must directly wait for the backend service consumer to complete its task, any slowdown or failure in the consumer directly impacts the client, making the system incredibly fragile. There's a significant loss of data if not buffered properly. If a service is overwhelmed and cannot process incoming requests fast enough, unbuffered requests might simply be dropped and lost. Fundamentally, queues enable you to build resilient, scalable, and decentralized systems by providing a robust buffering and communication layer that tolerates failures and handles variable load gracefully. To summarize our deep dive into queuing systems and asynchronous design, queuing systems are fundamental for enabling decoupling, buffering, and resiliency in distributed applications. They are utilized in virtually all real-world scalable architectures, from the massive video infrastructure of YouTube and the dynamic ride-sharing of Uber to the vast e-commerce operations of Amazon. Powerful tools like Apache Kafka, RabbitMQ, and Amazon SQS dominate production environments, offering various capabilities for different messaging needs. Understanding queues is critical for designing asynchronous workflows and enabling graceful degradation of services under pressure. Ultimately, queuing systems are a system design essential, a concept you must master both for whiteboard interviews and for building robust, real-world infrastructure. Before you go, I'd love to hear from you in the comments. If you found this video helpful, do give it a like. Share it with your friends, and of course don't forget to subscribe to the channel to help us grow. I will see you in the next one. Till then, happy learning.